Today is the sixth lecture. To give you a summary of what we have done yesterday. Yesterday we discussed about so-called the condition for the translational equilibrium and the condition for the rotational equilibrium. We have made use of these concepts to discuss a few problems, and in this process we also came across the concept of the center of gravity and its relation to the center of mass problem. Today we will continue further. So far we have been seeing the rotational motion is somewhat similar to linear motion. Equations 5, for example, what is known as velocity in the case of linear motion, its role is taken over by angular velocity d theta by dt, etc. The linear acceleration is dv by dt, and the angular acceleration is d omega by dt, etc. Today we will continue further. So far we have not asked rather a very important question. In the case of linear motion, you have mass, the concept of mass, which comes in Newton's equation everywhere, and who takes the role of the linear mass in the rotational motion. And so today's topic for discussion is moment of inertia. Basically this particular lecture, moment of inertia, and there are two rather important theorems, and what I'll call it as parallel and perpendicular axis theorems. This is what we are going to focus on. And so the question which I already asked is what is the analog of mass? Analog of mass, usually it is denoted by m in rotational motion. This is the I won't call it as a motivation. This is an intriguing question which everybody should ask. It will come very naturally, and we see what is the answer for it. And so there's one more thing. Even yesterday we had seen rotation of a rigid body, and then hereafter we are going to consider rotation about a fixed axis, and this is very important. So rotation about a fixed axis. That's what we are going to consider. The general rotation of a rigid body in all possible axis is considered a topic for advanced study. We are not going to consider it. And so what we have is let us say a rigid body. It is one axis. This is a fixed axis, and you consider a particle here, and then it will be making a circular motion. Its radius is, let us say, Ri. This particle has got a mass mi here, right? Then the kinetic energy K, the kinetic energy of the rotating body, I will denote it by capital K. This is equal to, so this whole body is can be viewed as different masses, m1, m2, etc. I am considering a typical mass which is located at a distance Ri from the fixed axis, and it at a distance. So the kinetic energy of this particular object is, I can consider this as sum of all the kinetic energies. I am not indicating I runs over what? Over all particles. This is equal to half of sum of sigma over I mi, this is what is velocity? This is vi, ri, omega. This is whole squared, right? So half mv squared, v is omega cross r. This is perpendicular. We will have ri and ri times omega, and omega is the same for every particle within this rigid body, and whereas this ri, the distances will change. So this is equal to half of omega squared is common, and you are simply left with summation over I mi Ra squared, and this is the quantity which is known as the moment of inertia. So moment of inertia of a rigid body is simply sigma or summation over mi Ra squared, where Ra is the distance from a fixed axis. And so always talk about moment of inertia of a body about an axis. That is important. I can also consider the moment of inertia of same body about some other axis. So there is no point in simply mentioning what is the moment of inertia of a sphere or any object. You should say that the question you should ask is what is the moment of inertia of a body about an axis, and that is very important, right? Okay, this is something, this equation is this is usually denoted by I. Therefore I have K, the total kinetic energy, is equal to half of I omega squared. This equation reminds us of this is something similar to in the case of linear motion, we say that half m v squared. So therefore the when you see this equation, immediately a bell should ring in your mind. What is that? You would like to compare this in the case of linear motion. The expression for kinetic energy is half mv squared. This is something similar to that, right? Now we are going to consider there are certain important properties of moment of inertia. So that is the next topic for discussion. So properties of moment of inertia. I, the symbol is there for moment of inertia. I simply call it as this. First one. First thing is the kinetic energy of the moment of inertia of a body does not depend on omega, namely the angular velocity. Does not depend on then what does it depend on? It depends on mass. It depends on actually mass distribution, rather to say. So mass distribution in terms of shape and size. Okay, this is the first property. Then second property, and it's a characteristic of the rigid body. It is a characteristic. It's very typical to each rigid body, characteristic of a rigid body. Then and also not only that, and also about an axis, also an axis about which it rotates. It means the rigid body rotates. Now, just like mass is considered to be the measure of inertia of a particle or a body, similarly, moment of inertia is a measure of the rotational inertia. In the case of linear motion, you can call it as it's a measure of translational inertia. Here it is a measure of inertia in rotational motion. It's a measure of inertia in rotational motion. And as I already told, it is better to keep in mind that it is also a measure, it also depends on mass, shape, size, distribution of mass. Then one more property is there. It says the mass does not depend on any axis or anything. So here it depends on the nature of rotation about an axis. Nature of rotation about an axis. Then it is good to do this exercise whenever you come across any physical quantity first time for the new. It is better to write down its units and dimensions. What are its dimensions? The mass times L square. So therefore the units now in CGS units kilogram meter square. And remember, it's a scalar quantity. It's a scalar quantity that we need to keep in mind. Next. We will proceed to calculate moment of inertia of a few of certain objects which we come across very frequently in physics. First, thin circular ring. This is the first one. Thin circular ring. So I have a circular ring like this. It's a fairly simple calculation. Then I need to indicate an axis. Axis is passing through the center. So its radius of the ring is r. At this, let us say that the total, this is the axis of rotation, and total mass is m. Now I take a typical point here, and let us say that mi is the mass. Now what is the definition of moment of inertia? It's a small element. I'll take definition of moment of inertia is mi ra squared. So here this so every point on this circular ring is a distance r. Therefore, let us say that mass element is mi ra squared. This is equal to r squared times summation mi. Summation mi is the total mass of the particle. Therefore, this is m r squared. So this is nothing but adding all the masses which are located on this ring. So moment of inertia of a circular ring about an axis passing through its center in a plane perpendicular to the plane of the circular ring. That is important. Okay, I am considering an axis which is perpendicular to the plane of the circle, and it also passes through the center. So this is the moment of inertia. Now, as I told you, we are going to consider few examples. We will have one more, one simple example as an illustration. I'm looking for some space. Yes, I have here. Suppose I have here three masses. Maybe I'll divide this into two. I can save the space. So I have here a triangle. Okay, it's an equilateral triangle. A, I have M1 is equal to M, and M2 is equal to M here at the vertices. M3 is equal to M. So what is the axis I am considering? Axis I am considering is the altitude. So therefore it is A by 2. This is A by 2 here. So moment of inertia of this triangular lamina, it's not a lamina, sorry. The moment of inertia of these three masses located at the vertices of this equilateral triangle. So I altitude. What is the meaning of I sub altitude? Means moment of inertia of these three masses about this particular altitude is m1 into 0 squared plus m2 into, from the axis it is a by 2 whole squared plus again m3 into, this is located at a distance of a by 2 whole squared. So therefore this is equal to 2 times m into a by 2 the whole squared. Therefore it is ma squared by 2. It's a simple calculation to illustrate that how a moment of inertia of a distribution is calculated. Now we'll consider the second example. Remember, we are calculating the moment of inertia, moments of inertia of various objects which we regularly come across, and we are going to make use of this. Next is moment of inertia of a rod. Uniform rod of uniform cross section of mass is uniformly distributed. So I am going to consider an axis which is passing through the center of mass. This is the axis. Suppose I consider this as this will come little later. This will come little later. What I will do is I will put masses here, m here, m here. Sorry, it is this is a massless rod. Sorry, it's a massless rod. Light rod. At the two ends of it we have two masses, m1 and m2, and then I want to calculate the moment of inertia of this. This in principle it is almost same as this. So moment of inertia about this axis indicate m into L by 2 the whole squared. This is L by 2, this distance is L by 2 plus m into L by 2 the whole squared. Therefore it will be m L squared by 2. So this is almost same as this. Only thing is the moment of inertia of the this figure is turns out to be the same because we are considering the axis passing through m1. Okay. Now there is a concept called radius of gyration. The radius of gyration is like this. So one thing is clear, whenever you calculate moment of inertia of any object, there is going to be a mass term times a quantity which has length squared. There may be some proportionality constants. There may be certain objects which are going to be numbers. So I will just call it as number. Now you treat this whole thing as mk squared. So then you have to calculate k for each of these cases. Then k is called as radius of gyration. Why? What is the idea? What this means is that about a particular point, the whole the mass of the whole body is located at here at a distance of k, because whenever you have moment of inertia to be mk squared, what it means, there is a mass m which is located from the axis or from a fixed point O at a particular distance k. And so the moment of inertia is either expressed as it is or in terms of radius of gyration, and we will see in problems. And for example, in this case, when I write it as mk squared, then the radius of gyration k is equal to L by root 2. Okay. Now we will consider the third example. The moment of inertia of a rod, which is uniform rod about an axis which is at the one end. And so it's a uniform rod. Rod of uniform cross section. So there is a concept called mass per unit length. The whole length of the rod is L, let us say. So what I will do, I will consider an element here. This is at a distance x, dx. Okay. Now rho is the mass per unit length. It is one dimensional, therefore it is the mass per unit length we consider. This is the axis of rotation. Okay, therefore if rho is the mass per unit length, what is the total mass? Total mass is length times mass per unit length. Now moment of inertia of this element, this particular element dx is equal to, let us say there is whatever is the mass here, that times x square. The small element is located at a distance of x. Now what is dm? It is dx times rho times x square. Now I want to calculate the total moment of inertia, therefore I have to integrate it. Rho x square dx, and at this end it is x is equal to 0. At this end it is x is equal to L. Therefore I have to integrate between 0 to L. So rho into x cube by 3, therefore L cube by 3. This I can write rho L into L squared by 3. Rho L is m, therefore m L squared by 3. So m L squared by 3 is the moment of inertia of a uniform rod of length L about an axis which is located at one end. Right? Then next one, we will move a little faster. Now we will calculate the moment of inertia of a rod, uniform rod, about an axis passing through the center. This is L by 2. This is L by 2. Therefore this I can view it as moment of inertia of two rods, each rod about an end of the rod. Therefore it is is equal to m by 2 into L by 2 whole squared by 3 into 2. Therefore it is ml squared by 12. Fine. We are going to calculate moment of inertia of a few more objects. Therefore I will divide this space. So now moment of inertia of a circular disc. It's a circular disc. Moment of inertia of a circular disc. So I have a circular disc. So this is the center. Okay, now what I will consider, this radius is capital R, its radius is R. I will consider a typical disc here. It has an annular space. If I take this as R, then this annular portion has a width dr. So I consider the moment of inertia to be, now what is the circumference of this? It is 2 pi r. 2 pi r. Then area is dr. Then what is the mass of this? This is area into mass per unit area. Rho is the mass per unit area. Mass per unit area of the material. And that times this mass is located at a distance of r squared. Therefore, I is equal to 2 pi rho. I can take out integral rho cubed dr, r going from 0 to capital R. So this is equal to pi rho r to the power of 4 by 2. This is equal to mr squared by 2. Why? The total m is equal to, what is the mass of the disc? Area into mass per unit area. Therefore, from here I can split it out, pi r squared rho. One pi is missing here. I can write pi r squared rho will become m, the remaining terms. Right? So like this we have to, now that of a solid cylinder. Similarly, you can calculate moment of inertia of a solid cylinder, which I am not going to do it. I of a solid cylinder about an axis passing through the, about an axis passing through the center. About an axis passing through the center. Passing through the axis of the cylinder. This we can work it out. This is again is mr squared by 2. Now I will do this calculation for hollow cylinder. Okay. So I have this hollow cylinder like this, finite hollow cylinder, and then this is the axis. Okay. Now I will consider a small element. It's a hollow cylinder. It's a what I call a circular strip band rather, which is lying on this cylinder. And now what is the length of this? Length of this is 2 pi r, because the radius is r, and then this length, this is of width dl I will take. Then this hollow cylinder, this is of area. Therefore, the mass per unit area I will take it as rho, mass per unit area, and let me say that this height of the cylinder is h. I will take the length of the cylinder rather. Okay, this rho, and this is located at a distance of r squared. So this is what is di. So if I want to have I have to integrate it. So when I integrate it, what will I get? 2 I can take out, pi I can take out, r I can take out, rho, this is r cube, integral dl is simply L. Therefore 2 pi r cube rho L. Okay. Now what is the mass of the cylinder? Mass of the cylinder is two pi r is the circumference, that into L into rho. So this is 2 pi r L rho. So 2 pi r L rho, if I factorize, it is 2 pi r L rho into r squared. Therefore it is m r squared. This is what I will call it as m. The same way you can calculate moment of inertia of various objects, but I am going to do the moment of inertia of one object, then we will proceed further. So this is the moment of inertia of a solid sphere. Is an important quantity. We will be using it again and again. So I have a solid sphere about an axis passing through the center. So I have a what I consider. So this I don't need perhaps. Oh. No. Right. Now I will consider a small sphere. I'll consider a sphere. I'll consider a sphere of radius r and small increment dr, and consider this portion. So what I will have, this surface area of the smaller sphere is 4 pi r squared. Therefore the volume of this region is 4 pi r squared dr, and mass of this region is 4 pi r square dr times rho. This whole thing is located at a distance of r. So I want the moment of inertia, therefore I want to integrate it. This is r squared, sorry, I forgot that. So this will be 4 pi 0 to r integration. R to the power of 4, therefore it will be r to the power of 5 by 5 and rho. What is the mass of the sphere? Mass of the sphere, volume 4 by 3 pi r cube times rho. Therefore I can write this I in terms of, I can factorize this in terms of, I will have 3m 3 by 5 m r squared. Okay. This is the moment of inertia of a sphere about an axis passing through the center. Now we are going to have, we will consider two important theorems. One is called as, there are two important theorems which are repeatedly used in the calculation of moment of inertia problems. One is called as perpendicular axis theorem. This is valid for planar objects. This is valid for planar objects. We state the theorem, and proof is not necessary at this stage. However, not complicated. One can learn from some advanced books. Now, what it says is, suppose I have a planar object. It has three axes: x-axis, y-axis, and z-axis. I want the moment of inertia of this planar object. One wants the moment of inertia of the planar objects about the z-axis. This is equal to, what it says is, you need to consider two axes perpendicular passing through the planar object. Then this is, one is this Ix, another is this moment of inertia about this y. In other words, if I want the moment of inertia of a planar object passing through an axis perpendicular to the plane of the object, then one needs to consider two perpendicular directions which are concurrent with this axis located on the body. Then if I know the moment of inertia of this is, let us say, this is Ix, if I know, then Iy here I know, then I know the moment of inertia about z. That's the idea. So the the moment of inertia, the mi of a planar body about an axis perpendicular to its plane is equal to the sum of moment of inertias about the two perpendicular axes, about the two perpendicular axes concurrent with the perpendicular axis and lying in the plane. Now we will, as I told you, proof is not required, but we will make use of it. I will give you two illustrations. Suppose I consider example 1. I consider circular disc. Right? We have so I have a circular disc, and x, y, z. Right? So I want the moment of inertia about z axis. That's what I want, Iz. This is same as moment of inertia about Ix, moment of inertia about yi. These two I have to add. Right? So Iz, I know what is the moment of inertia about z axis of a circular disc, where we have calculated earlier of a circular disc, that we have calculated as mr square by 2 moment of inertia of a circular disc. Therefore Iz I know, but I don't know what is Ix. Ix and Iy, you remember this diameter is symmetric, it divides the circle into two. Therefore moment of inertia Ix should be same as moment of inertia Iy. Therefore 2 times moment of inertia of Ix is same as 2 times moment of inertia of Iy. This is equal to mr squared by 2. So this implies Ix is equal to Iy is equal to mr squared by 4. Right? Now I will do one more simple problem. So it makes our life easy if I want to calculate the moment of inertia of the circular disc about this axis, x-axis or y-axis. Now circular ring, one more example. Circular ring. Again, no, the moment of inertia of a circular ring we have calculated. Circular ring, x-axis, y-axis, z-axis, I need not write everything. Circular ring, I think we have already done. Moment of inertia of a circular ring, where is it? Probably that was this. Circular ring, first we did mr squared. That was the first example we considered. Moment of inertia of a thin circular ring. This is mr squared. So therefore Iz is equal to mr squared. So what do we have? Moment of inertia of x plus moment of inertia of y. Perpendicular axis theorem, this must be same as moment of inertia. This by symmetry, 2 times Ix is equal to mr squared. Therefore Ix is equal to Iy is equal to mr squared by 2. Next we have to discuss what is known as parallel axis theorem. Parallel axis theorem. What the parallel axis theorem says is, before it is applicable to body of arbitrary shape, applicable to body of arbitrary shape. Unlike the perpendicular axis theorem, which is valid only for planar objects. And so what we are going to do is that the idea is this is a solid. What we want is that now we want the moment of, given the moment of passing, suppose this is the center, this is the center, let's say center of mass, this is Cm of this object. Given the moment of inertia about the center of mass, about an axis passing through the center of mass, I want the moment of inertia of the object about some line L, let us say. This is known. We want to calculate moment of inertia about L. This is equal to what? Answer is provided by so-called this parallel axis theorem. What it says is that IL is equal to suppose I call this as z-axis, this I will call it as let us say z prime, z prime, z prime is equal to Iz I sub z plus mass of the object, then the perpendicular distance between them. Right. Let me again repeat. I know the moment of inertia of this object about an axis passing through the center of mass. Then I want to calculate, if one wants to know the moment of inertia of the same object about some other axis, let us say this is the z prime, then the moment of inertia about z prime is same as the moment of inertia of the object passing through about an axis passing through the center plus this particular the product of mass into the distance between, square of the distance between them. Okay. Now we need to fix the axis if you require, just x-axis here and y-axis here, just in order to avoid confusion somewhere. Right. Now we will do 2 examples. First, an example 1. Is already known. This is z axis, this is L by 2, this is L by 2. I want the moment of inertia about the line which is this z prime from one end. In other words, given the moment of inertia of a rod about an axis passing through the center, I want to calculate the moment of inertia of the rod about an axis which is passing through the one end of the rod, but both these axes are parallel. That is the situation, right? Then Iz prime is equal to we had we have Iz we had calculated. Sorry, Iz is ml squared by 2, ml squared by 12, which we had calculated. Where we had calculated this. This was the example. This is ml squared by 12. Now I want the moment of inertia about z prime. So moment of inertia I about z prime is equal to Iz plus total mass is m. Distance between these two lines is L by 2 whole square. Iz is ml squared by 12 plus ml squared by 4. So this is ml squared by, this is 4 12 1 3 4 ml squared by 3. This we had done. Moment of inertia of a rod about an axis passing through one end. This calculation we have done. So it is a very simple verification of perpendicular axis theorem. So one more illustration we will do. One more illustration we will do that. Now I will consider circular ring, moment of inertia of a circular ring. Example, circular ring about a tangent. So I have a circular ring, okay, this is the diameter, I have a tangent. This is the tangent I will call I tangent. Okay, so for this now I need to know the moment of inertia about the diameter, I dia. Right. Now I need two perpendicular axes. So one axis here, other axis have to, let us say that I will just indicate it here, like this. I don't need this. Oh my God. So we have to be careful with the diagrams. So this is the I. Okay, I diameter. So by perpendicular axis theorem, 2 times I diameter is equal to mr square. This we have already done. Therefore, I diameter. What is mr square? Mr square is the moment of inertia of the circular ring about an axis which is perpendicular to the plane of the circular ring. That is mr square. From this I am calculating the moment of inertia of about the diameter. This is equal to mr squared by 2. So here I have made use of perpendicular axis theorem. Now I need to know the moment of inertia of this circular ring about this tangent. So I tangent. Now I will make use of parallel axis theorem because I know the moment of inertia about the center. Right, is equal to, what is that I want? Is equal about an axis mr squared by 2. This is, I will write a step, therefore it will be I about a diameter plus mass into distance between these two lines is r, so r squared. So this is equal to mr squared by 2 plus mr squared. This is equal to m into r squared by 3. This is an interesting problem in the sense that we are making use of both the this is parallel axis theorem. Here we are making use of both the theorems. Okay, so in this case we are going to see some more examples at a later stage. Let me repeat what we have done in this problem. I want to calculate the moment of inertia of this circular ring about the tangent. I have to make use of parallel axis theorem. I can. For that I need to know the moment of inertia of the circular ring about the diameter. That we have not calculated. So what is that we know? We know the moment of inertia of the circular ring about an axis which is perpendicular passing through the center. Okay, that is what is we have it. Therefore I have that is mr squared. Therefore the I about diameter, moment of inertia about diameter is mr squared by 2. Now I can calculate the moment of inertia about the tangent. It is moment of inertia about diameter plus mass times the square of the distance between these two parallel lines, mr squared. Therefore mr squared by 3. And to summarize, what we have done is we found that the moment of inertia is the concept of moment of inertia is the rotational analog of mass in linear motion, and then we have calculated the moment of inertia of various objects, and we have also seen two rather very important theorems which are repeatedly one makes use of, so-called the perpendicular axis theorem and parallel axis theorem. The perpendicular axis theorem is valid for planar objects. Parallel axis theorem is valid for object of any arbitrary shape and size. Only thing we need to know the moment of inertia of about an axis passing through the center of mass of that systems. Life is very simple if the systems are symmetric, and we will see in next class.